K3 centripetal and tangential acceleration. We did this problem before where I was spinning something around at a distance r away, and v, the tangential velocity v, is equal to omega r. But before I got to that stage, I had angular acceleration to get it going faster and faster. And then once when I got it at the speed I wanted, the velocity v, the speed is constant, but the direction changes. So since the motion is looking, say, from the top, since the motion is changing its direction, it's circular, that the force on the string pulls in, and that force that's pulling in, the centripetal force, is equal to the mass times the centripetal acceleration, which is mv squared over r. So you get acceleration of the centripetal type when you have a velocity that's making something go in a circle, and in this case the velocity is constant, so that's all you have. But when I was getting this to go faster and faster, I also had tangential acceleration. So let's look at that. Let's call this one here the centripetal acceleration. That's this one, a little c. And then let's have here, let's put a little t. And this is the tangential. You could also call this radial, like a radial acceleration if you want. And if you pick the radial direction to be positive outward, then AR would be actually negative. So different notations are used. We'll just simply look at AC for now, the magnitude. And AT is the angular acceleration, and that's equal to alpha times r. And that's a tangential acceleration. That's the acceleration that's tangent to the circular path. So if we draw another picture here, where this is the radius r, we can here draw a vector going up for the tangential acceleration, some mass here. And then here, I'm going to put the direction in this way. This is toward the center. It's always the case with the centripetal acceleration, it's going to be toward the center. So if I draw toward the center, I can then draw a little vector sign like that, and then like here's the vector, and like there's that vector. Now the total acceleration, what you would do is add the two vectors. So if we have the tangential one going up like this, and we have here the centripetal one, if we draw a little rectangle there, if we add this vector, we go up, say, toward the north like that, and then we go to the west, that the total vector would be this one here. So this is the total acceleration, which you can write down as the centripetal vector plus the tangential one, like this. And then the angle here, if you want to find this angle, theta, the tangent of that angle is equal to AT. This is AT, the other side of that rectangle, and then you divide by the magnitude AC, like that. And that gets you the angle. What I would like to do is a real life problem now, where there's a race car. It's actually coming this way. It's going to be doing something like this. And there's a center of the curvature like this. And we can take it to be, the car is like right here. going that way. So we have a radius of curvature, and we have the velocity. We'd have some values that the r is 50.0 meters, and the velocity for the racing car is 175 kilometers per hour. And the acceleration, looking at the speedometer, this is the tangential acceleration. This is 20 kilometers per hour per second. And we're going to use G to be 9.81 as the given in this problem. So we go for 3 significant figures. And here's a photograph of the situation. So this racing car is heading, say, this way, and there's like this center going that way. So your R going that way, and the R is going to be 50 meters. And here's a velocity, and there's an acceleration, tangential acceleration. So if we look at this to plug in some numbers, and first convert, I want meters per second, so I don't want to have this kilometers per hour in there. So if we look at 175 kilometers per hour, we're going to convert this by saying there's 1,000. Well, let's go ahead and say that's equal. And we'll put in 1,000 for the kilometers, and we'll put in 3,600 for the seconds. We're simply writing this number down. So if we do that, we will get 48.6111, like the round off last, meters per second. Then for the tangential acceleration, 20.0 kilometers per hour second. And here's where the units really help out. We put the number down, and then for the kilometers, I'm going to have 1,000 meters. And then for this first hour, I'm going to have 3,600 seconds. Then the other seconds hanging around. And that's going to give me meters per second squared. When I work this out, I get 5.555, something like lots of fives, 6 meters per second squared. Now, we're interested in g-force. And g-force, you simply want the acceleration in terms of how many g's you got. So let's do here, let's say we're going to find for the centripetal, the centripetal case, let's find what the g is. So here we would take the centripetal acceleration and divide by g to find how many g's. That's 1 over g, and you have, for the centripetal acceleration, you just have v squared over r. So that's v squared over r. So that's 1 over 9.81. And this will basically be a number like 3 g's or 4, it's a number, a ratio. So this would be here, we put in this thing, the 48.6111 squared, and then you divide by the 50.0, and you get 4.8176. If you want to write this out, that the acceleration is 4.82 g. So that's a lot, see? And then here we know that's toward the center. So that's going to be toward the center, like this door will then like push on the rider. You feel like you're pressed up against the door. The door is like pushing you in toward the center. Then we'll do the next for the tangential, which is the forward acceleration. That's this one here. The acceleration is tangent, the tangent. So here we would take the tangential acceleration divided by g, and that would be going up to this equation, say. So now you want the 5.55556 thing, and that's the acceleration, that's it, that's all you gotta do. Divide by 9.81, and you get 0.56632. So the tangential acceleration, or the forward acceleration, is quite small. The driver would feel the seat pushing on the driver's back. So there are the accelerations. Now, notice that the acceleration due to the centripetal case is a lot bigger. It's a lot bigger than the tangential acceleration. It's like almost 10 times, bigger, The last thing we like to do is find the total acceleration. We have a centripetal acceleration going toward the center, and then the forward direction. We have the tangential acceleration, and we're assuming this is a perfect circle, so that's a right angle. And you can make a rectangle here, and we can find then the total. If we went from here to there, see, the total would be along the diagonal. And this is a right angle from this perspective. So therefore we want to square this one and square this one, add them together and take the square root. So this is the Pythagorean Theorem. This is the square root of AC squared plus AT squared. So when you do that, since the AT is fairly small, you're going to just get mostly the AC. When you work this out, this is 4.85 G. So it just went up a little bit due to this component down here being small. So here's the angle relative to going straight, this angle there. That tangent of that angle is this one here, which is your AC, over the AT. And the AC is the big one. So this is here 4.82 over 0.5. It's close to 10. So when you do that, and you put this in for AC, 4.82. Actually, I put in more significant figures and round off last in the text, and this 0.566. Say G, the G's cancel, and the angle comes out to be 83.3 degrees. So the angle is essentially 90 degrees. It's like toward the center of the circle. And here it is in the text, showing you the forward acceleration and toward the center acceleration, and then making yourself a rectangle where then you could find this angle relative to the forward direction as this magnitude's AC, this magnitude's AT, so the tangent of theta is AC over AT, and that's almost 10. When you put those numbers in, this is the 4.8176 rounded off last, and the 0.56632. You can see 5 over 0.5 is almost 10. So when you take the arctangent, you get the 83 degrees. So the driver is looking straight ahead and turn almost 90 is your resultant acceleration vector. So it's a nice problem.